Plus, am I audible? Hello,
Yes, sir.
and the screen is visible?
Yes, sir. Visible.
Okay. Okay, in the previous class, we have started the design of sidewall of bunker. In that, we have calculated the lateral pressure acting on the sidewall. That is pH equal to 24.73. And after that, we have also assumed the thickness of the sidewall. The thickness of the sidewall can be taken between 150, 180, or you can also take 200 mm. So here we will take it as 180 mm. Okay. So whatever pressure, lateral pressure you have gotten, it has to be factored. So you have to find the factored lateral pressure Pu equal to 1.5 into pH. So whatever lateral pressure you have gotten, that has to be factored. So when you are multiplying 1.5 to pH, you're getting 37.08 kilonewton per meter square. And also you see the span, the size of the bunker is 3 meter. Okay, this is 3 meter. But we are very much interested in the effective span, that is center to center distance between the wall of the side wall. Okay, so 3 plus 180 divided by 2, 3 plus 180 divided by 2. Okay, so the effective span that you're getting is 3.18 meter. Now we can find the bending moment, the negative bending moment, and the positive bending moment for the side wall. Already I have given you the formula. The same formula we shall be using to find the bending moment at the corner, that is negative bending moment, and bending moment at the midspan, that is positive bending moment. And see to it that the bunker that we are dealing with, it is not a rectangular bunker, it is a square bunker. Okay, so we can modify the formula. Whatever formula we have written in our discussion in the derivation, that is for the rectangular bunker. But here we are having the circular bunker. Those formulas can be little bit modified. Okay. So maximum negative bending moment, maximum negative bending moment, maximum negative bending moment is given by mu equal to pu L effective square divided by 12. Okay. So pu is 37.08. L effective just now you have calculated, that is 3.18 square divided by 12. Okay, so negative bending moment, or the bending moment, uh, sorry, bending moment at the corner is 31.24 kilonewton meter. See, with in the side wall, you have bending moment, and you also have direct tension. So because of the lateral pressure, there will be tension in the wall. That tension also you need to find. Okay, so force, tensile force, Pu equal to Pu into L effective divided by 2. So this is the formula of direct tension, that is tensile force. Pu we know 37.08 into L effective is 3.18 divided by 2. Okay. So direct tension Tu is you are getting it as 58.6 96 kilonewton. Okay. And you see, you also have bending moment with respect to the tensile force. Like, for example, this is your wall, 180 mm wall. Okay. And you're providing reinforcement here. This is where you're providing reinforcement, and the effective cover is 30 mm. We will assume that effective cover is 30 mm. And tensile force is acting at the middle of the wall. Okay. So this is your tensile force. And this tensile force will create bending moment with respect to this reinforcement. I will take this as X. Okay. So this is from middle to the, at this point, it is 180 by 2. 180 by 2 minus 30, you will get X. Okay, so the point is that the tensile force will also create bending moment, and that bending moment will be opposite to whatever bending moment we are calculating. So we need to calculate the bending moment with respect to the tensile force, and the bending moment with respect to the tensile force is opposite to the normal bending moment. Okay, so I will write here bending moment or moment due to tensile force. Due to tensile force. Okay, so this is equal to Tu into x. What is x? Here I have shown you. This distance is x. Okay, x. How you will calculate x? X equal to 180 by 2 minus effective cover, that is 30 mm. So this is, you are getting this as, 60 mm. 60 mm. Just note down the unit. Okay, 60 mm. So TU you got, TU is 58.96, 58.96 into x. X is in mm. Here you can write down in meter. 0.06, 0.06. This is equal to 3.54 kilonewton meter. So whatever bending moment we have gotten, it is with respect to the tensile force, and I already told you the bending moment with respect to the tensile force is opposite to the normal bending moment. Okay, so after calculating this, you have to find the net bending moment. Net bending moment at corner. Net bending moment at corner equal to 31.24. This is what you have gotten, minus bending moment with respect to the tensile force, because it is opposite to the normal bending moment, 3.54. So the net bending moment at the corner that you're getting it as 27.70 kilonewton meter. Okay, so this is the net bending moment at the corner. You also have to find the positive bending moment. This is the negative bending moment that we have gotten, and that is at the corner. That is hogging bending moment. Okay. You also have to find the bending moment at the midspan, and we know the formula to find the bending moment at the midspan. It is PL square by 24. Okay. Maximum bending moment. Maximum bending moment at midspan. At midspan. That is equal to PU into L effective square divided by 20. Okay, so this is coming as, you can substitute the value of Pu. L effective is 3.18 divided by 24. So you are getting it as 15.62 kilonewton meter. Okay, and again, net bending moment as also has to be calculated at the midspan. The bending moment with respect to the tensile force has to be, subtracted. So the net bending moment at midspan is given as net bending moment at the midspan equal to 15.62 minus 3.54. Okay, so this is coming as 12.08 kilonewton meter. Okay, now we know the depth of the wall. Depth of the wall or thickness of the wall is 180 mm. And the wall has to be considered as slab. How you are designing the slab, in the same way wall has to be designed. The wall of the bunker is similar to the design of slab in case of building, in case of normal building. Okay. So the 180 mm is overall depth of the wall. But we are interested in small d, that is effective depth. Okay. And already we have assumed 30 mm as effective cover. Since we know the effective cover, we can find effective depth. Okay. So small d equal to capital D minus effective cover. So capital D is 180 mm minus effective cover is 30. Small d is 150 mm. This is your small d. Now, whatever depth we have assumed for the wall or for the slab for that matter, it has to be checked whether that depth is safe or not. So how we are doing that? In the slab, mu is equated to mu. In the same way, we need to perform the same action in the bunker. Mu is equated to mu and mu depends on the grade of steel. Okay, for the grade of steel that we are using in this design is Fe415. For Fe415, the formula of mu is 0.138 FCK BD square. Okay, and the bending moment that we need to use the maximum bending moment. We got two net bending moment. Okay, the net bending moment at the midspan and the net bending moment at the corner. So which one is maximum? The maximum net bending moment is at the corner. Okay, so that bending moment we need to take. Okay, in Newton mm, 27.70 into 10 to the power 6, and mu is 0.138 FCK B E square. B has to be taken 1000 mm. In the slab, how we are assuming 1 meter width of the slab. In the same way, we are assuming 1 meter, width of the side wall. So this can be written as 138 FCK is 20 because we are using M20 grade concrete, and B is 1000. D we need to find. D required. We need to find. Okay. So D required, by solving this equation, D required is coming as 100.18. But what we have provided is 150 mm. Okay, so D provided is 150 mm. So whatever depth we have provided, it is okay. It is okay with respect to strength criteria. It is okay with respect to safety criteria. Okay. Okay. Since we are we are terming the side wall as that of slab, so AST minimum will be AST minimum, the minimum reinforcement that is provided in the slab or in the side wall is 0.12% of B into capital D. Okay, so 0.12%, 0.12 divided by 100 into P is 1000, and capital D is 180 mm. Capital D, overall depth of the slab or overall depth of the side wall. So the minimum reinforcement is coming as 216 mm square. So whatever reinforcement that we will be calculating based on bending moment, it has to be greater than minimum reinforcement. If it is not greater than minimum reinforcement, then we have to provide minimum reinforcement. Okay, this point is clear. Okay, so we will provide the AST with respect to the bending moment. So AST at the corner, we have corner bending moment, AST at corner. The formula of AST is 0.5 FCK into B into small d divided by Fy bracket 1 minus under root 1 minus 4.59 mu divided by FCK B d small d square. So by this formula, we will get AST with respect to the bending moment. Okay, so we are interested in the AST to find at the corner. Okay, so we need to substitute the value of mu or whatever the thing that we have in the formula. 0.5 into FCK is 20, B is 1000, and small d is 150 mm divided by Fy, that is 415. Okay, 1 minus under root 1 minus 4.59 mu for the corner. Already we have calculated, that is 27.70 kilonewton meter. But here in the formula, mu, the bending moment, has to be written in Newton mm. Okay, so how to write in Newton mm? I will tell you. 27.70 into 10 to the power 6 divided by FCK, that is 20 into 1000 into 150 square. So this is that we have in the formula. You can find AST for the corner. AST for the corner is 552.90 mm square. Okay. And I told you, we also have tension in the side wall. And because of tension, because of direct tension, you also have to find the reinforcement to resist the direct tension. So the formula of AST for direct tension is AST for direct tension, I will write here, for direct tension equal to TU divided by 0.87 Fy. And TU, we know, we have calculated TU 58.96 into 10 to the power 3 divided by 0.87 into 415. Okay, so AST for direct tension is given as 163.30. Okay, and total AST we have calculated at the corner with respect to the bending moment, and after that we have calculated AST for the direct tension. And what is our point? The point is that we need to have the total AST of bending moment plus AST of direct tension. Okay, so total AST. This is for the corners. Okay, we have not yet come to the midspan. This is for the corner. 552.90 plus 163.30. The total AST that we are getting it as 716.2 mm square. Okay, and it is greater than the minimum reinforcement. The minimum reinforcement is 216 mm square. So what we are getting for the corners AST for the corner is 716, which is more than the minimum reinforcement. Okay, and we can assume some bars. Try 12 mm bar. Try 12 mm bar. Okay, if you're trying 12 mm bar, how to find the spacing? You know how to find the spacing in the slab. In the same manner, spacing has to be calculated in the sidewall design of bunker. Spacing equal to be width into area of one bar divided by AST equal to width is 1000 mm. Area of one bar, you are assuming 12 mm diameter bar. So area of that bar will be pi by 4 into 12 square divided by whatever AST you have gotten, 716.2. Okay. So the spacing that is coming as 157.93. Okay. But what you have to provide less than this. So you can write down here, provide 12 mm bar at the rate 150 mm center to center as horizontal reinforcement at corner, because we are designing it for the corners. Okay, as horizontal reinforcement at corner. Okay, similarly we need to find the AST for the midspan. So you know the bending moment for the midspan. MA for the midspan is the bending moment for the midspan is the net bending moment. You have to take the net bending moment. The net bending moment at the midspan is 12.08. Okay. And you can find AST for the midspan. Just have to substitute the bending moment. I told you the formula of AST. AST for the bending moment is given as 129.41 mm. Directly I'm writing the the value. You can refer this formula. So the formula I have given you, this formula you can refer. The only thing that you need to change MU. MU for the midspan. Okay? That is 12.08 into 10 to the power 6 into 10 to the power 6 Newton mm. Okay. So AST for this bending moment, AST you're getting it as 129.41 mm square. And AST for direct tension, AST for direct tension, that also has to be calculated. We have already calculated it. It will remain same. Okay. 163.30. This is for direct tension. So the total AST for the midspan is 292.71 mm square. Okay. And you can try 10 mm bar for the midspan. 10 mm bar. Okay. Try 10 mm bar, and what spacing you will get? You see, same formula you need to use for the spacing given in the formula of spacing. Spacing that you will get is 268.31, and whatever spacing you will be getting, that has to be less than 3D effective depth or 300 mm, whichever is lesser. It has to be less than that value. Okay, so you can provide for the midspan. I will tell you the detailing of the reinforcement when we complete the design. We are designing the side wall, and we are in the verge of completion of the side wall, design of the side wall. Okay, provide provide 10 diameter, 10 bar, sorry, not 10 bar, 10 mm diameter bar at the rate 260 mm center to center at midspan as horizontal reinforcement as horizontal reinforcement. Okay. Okay, so this is whatever the things that we have designed. It is for the horizontal reinforcement. So in the wall, you will also get vertical reinforcement. So this is the wall that you have. Horizontal reinforcement will be seen like this. Okay, this is the horizontal reinforcement in the wall. And you will also have vertical reinforcement. And the vertical reinforcement is nothing but the distribution steel in the side wall, like the minimum reinforcement. How you are providing distribution steel in the slab, in the same way, distribution steel has to be provided in the side wall. Okay, and that is the minimum reinforcement. And already we have calculated the minimum reinforcement. Okay, distribution steel, distribution steel that is vertical in the side wall, vertical reinforcement. Okay, so AST minimum has to be provided for the distribution steel, and already we have calculated the AST minimum, that is 216 mm square. Okay, and we can find the spacing for this AST. We need to assume the diameter of the bar. You can try 8 mm diameter of the bar for the distribution steel, and the spacing that you will be getting it as 232.71 mm. And uh, with respect to the distribution steel, the spacing has to be less than 5D, or it also has to be less than 300 mm, whichever is lesser. This is only with respect to the distribution steel. Okay, and you can provide 8 mm diameter bar at the rate 230 mm center to center as vertical reinforcement. As vertical reinforcement. Okay. So we have done the design of side wall. The next element that we have in the design of bunker is design of hopper bottom. The sloping slab which is at the bottom of the
सर
bunker. हाँ अब्दुल्ला.
सर वर्टिकल डायरेक्शन में डिस्ट्रीब्यूशन स्टील रहेगा अपना,
हाँ वर्टिकल डायरेक्शन में रहेगा.
और हॉरिजॉन्टल में मेन स्टील रहेगा सर.
हाँ क्योंकि फोर्स आपका हॉरिजॉन्टल है ना.
अच्छा, और सर
लैटरल
बंकर
प्रेशर
का
कैसा
हाइट
है?
अगर बंकर का हाइट अगर ज्यादा रहा तो फिर.
बंकर का हाइट ज्यादा रहेगा तो फिर तो साइलेंस हो जाएगा ना. उसका डिजाइन अलग है.
तो सर उसमें चेंज हो जाएगा, फिर वर्टिकल डायरेक्शन में मेन स्टील हो जाएगा.
नहीं नहीं वैसा नहीं है. जब मेन स्टील आपका हॉरिजॉन्टल डायरेक्शन में ही रहेगा,
अच्छा.
खास करके स्क्वायर और रेक्टेंगुलर बंकर में. क्योंकि आपका जो फोर्स है ना, फोर्स कहाँ से आ रहा है? हॉरिजॉन्टल डायरेक्शन से आ रहा है ना.
जी सर.
लैटरल प्रेशर कहाँ से आ रहा है?
जी जी सर, पर अगर बंकर का हाइट अगर ज्यादा ही रहा मतलब, तो फिर भी लेकिन वैसा ही होगा, सेम हॉरिजॉन्टल में मेन स्टील आएगा और वर्टिकल में डिस्ट्रीब्यूशन बार आएगा.
हाँ हाँ वैसे रहेगा. रेक्टेंगुलर और स्क्वायर बंकर में सर्कुलर का डिजाइन अलग है. तो मैं आपको नेक्स्ट जब ये खत्म हो जाएगा ना डिजाइन, सर्कुलर का मैं आपको
ओके सर.
बताऊंगा, उसका अलग है. रेक्टेंगुलर स्क्वायर में जो हॉरिजॉन्टल रेनफोर्समेंट रहेगा वो आपका मेन रेनफोर्समेंट रहेगा, क्योंकि ऊपर से नीचे तक रहता है वो,
ओके
पूरा
सर.
कवर करता है. ठीक है. और जो वर्टिकल बार्स रहेंगे वो डिस्ट्रीब्यूशन के बाहर रहेंगे. आपका बेंडिंग मोमेंट कैसा हो रहा है? बेंडिंग मोमेंट देखो, जैसे आप वाटर टैंक डिजाइन करते हो ना, बेंडिंग मोमेंट आपका ऐसा कुछ हो रहा है ना. ऐसा कुछ बेंडिंग मोमेंट हो रहा है ना. फॉर एग्जांपल ये पॉजिटिव रहेगा, ये नेगेटिव रहेगा. तो इसके लिए आप हॉरिजॉन्टल बार ही प्रोवाइड करोगे ना. ये प्लान है बंकर का. जैसे वाटर टैंक आपने डिजाइन किया है ना, वैसे ही आपको बंकर डिजाइन करना है. वाटर टैंक में भी आप देखोगे तो मेन स्टील आपके हॉरिजॉन्टल रहते हैं. ठीक है.
ओके सर, थैंक यू.
ओके. Okay, we have completed the design of side wall. Now we will switch over to the design of hopper bottom. Okay, design of hopper bottom. Already I have given you the formula. I will directly use the formula. Whatever the formula that I will be using in the design, it has been derived. So here I am directly using. If you don't know what happened in the previous class, so you will not get. Okay, so try to see the recording and come to the class. recording has been uploaded in the drive. You can see the recording and you can come to the next class. Okay. Design of hopper bottom. Third, design of hopper bottom. So first we need to find the load calculation. See, the hopper bottom is like this. It is like this. It is sloping slab. So in case of square or rectangular bunker, the sloping slab will be 4 in numbers. So one in either in this two direction and in the lateral direction. So you have 4 sloping slab. Try to understand this. How many sloping slab you have? You have 4 sloping slab in case of square bunkers. Okay. And the angle of the slope is theta, that is 45 degree. This is more or less constant in the case of bunkers. And the height that already we have calculated this height, it is 1.25. We need to find the length of the sloping slab. This is important, length of the sloping slab. So how we will find length of the sloping slab? We can use sine theta, length of sloping slab. We can use sine theta equal to 1.25 opposite divided by length of sloping slab. So length equal to 1.25 divided by sine 45. Okay. So length of the sloping slab is equal to 1.77. 1.77. Okay. We got the length of the sloping slab. And how many sloping slab you have? You have 4 number of sloping slab in case of rectangular or square bunkers. So we will find the self weight first. Self weight equal to mean length. I will tell you what is mean length. Mean length into 4. We have 4 number of sloping slab. Okay. I will tell you how to find mean length into length of the sloping slab. Length of the sloping slab. That is 1.77 have calculated. Sloping slab. Length of the sloping slab into thickness of the slab. So the thickness of the side wall is 180 mm. The same thickness we will take in the hopper bottom. The thickness of the hopper bottom is also 180 mm into density of the concrete. So this is your how to find the self weight of the sloping slab. What is mean length? I will tell you. See, this is how the hopper bottom is. The size of the opening is 0.5, and the size of the upper portion of the hopper bottom is 3 meter. Okay, so we are interested in the mean length because this is trapezium. In case of trapezium, we need to find the mean length. Okay, how to find the mean length? 3 plus 0.5 divided by 2. This is your mean length, and it is coming as what the value is 3 plus 0.5 divided by 2. It is coming as 1.75. 1.75. Okay, so mean length is 1.75. 1.75 into 4 because you have 4 sloping slabs into length of the sloping slab is 1.77. 1.77. Okay, that is length of sloping slab into thickness of the wall, thickness of the hopper bottom is 0.18 meter. 180 mm can be written in meter into 25 density of the concrete. Okay. So the self weight of the sloping slab is coming as 55.76 kilonewton. This is the self weight of the sloping slab, but it has to be, you need to take the total weight that is coming on the slab. The total weight that is coming on the slab is, you need to consider the weight of the coal in the bunker. What is the weight of the coal in the bunker? Okay. The second is weight of the coal. Weight of the coal. What is the weight of the material that is stored in the bunker? That weight also has to be taken when you're designing the sloping slab. Okay. So the weight that is coming on the sloping slab plus self weight of the sloping slab. So we have calculated the self weight. Now we will see what weight is coming on the slab. That is weight of the material. Weight of the coal. Weight of the coal. And we have seen in the previous class, weight is given 350 kilonewton, and we have changed the volume. So when we have changed the volume, weight is also increased. So weight of the coal is 352.40 kilonewton. And total weight is, the weight of the coal plus self weight, total is equal to 408.16 kilonewton. Okay. 408.16 kilonewton. But you see, this is the total weight, and there are 4 sloping slabs. 1, 2, 3 in this direction and 4 in other direction. If you see in the 3D, it will be like this. It will be like this. Okay, you have 4 sloping slabs. 1, 2, 3, 4. Okay, so this total weight, has to be divided, has to be distributed into 4 sloping slabs. So we need to find the weight on each sloping slab. So how to do that, I will tell you. There are 4 plates, okay? So weight on each plate. Weight on each plate of hopper bottom. Each plate means each sloping slab of hopper bottom. Okay, just tell me your attendance. Just pronounce your name, for the attendance. It will be, in the recording. Whosoever listening me, just, pronounce your name so that your attendance will
Hasid.
be recorded.
Abdullah Patel.
Next.
Hasim Aligar. Armash Bobde.
Who next?
Musa
Clear?
Burhan.
Musa Burhan. Next.
Sultan Sawadi.
Danish Khan.
Sultan. And next,
Danish Khan.
Danish Khan. Next,
Armash Bobde.
Armas Bobde.